On this one, a block is initially at position x equals 0 right here in contact with an uncompressed spring of negligible mass. The block is pushed along a frictionless surface from x equals 0 to x equals negative d, so from here to here, as shown above, compressing the spring by an amount of delta x is equal to d. That's the magnitude. It's, moved backwards, d. The block is then released at x equals 0. At x equals 0, the block enters the rough part of the track and eventually comes to rest at x equals 3d. The coefficient of kinetic friction between the block and the rough track is mu. So below it says, sketch the following two quantities as a function of the position of the block between x equals negative d and x equals 3d. Do not have to calculate values of the vertical axis, but the same vertical scale should be used for both. So they want the kinetic energy and the potential energy. I'm going to do the potential energy first because I think it's a little bit easier. So we know when we are fully compressed at negative d that we should be at some maximum amount of potential energy. And by the time we get to 0, when the spring is no longer compressed, that we're down to 0 potential energy in the system there. So we should start high, go low. The only question now is what should the shape of that be? Well, if you remember, the energy in a spring is 1/2 k x squared, where this is basically the compression distance. So that x squared tells us that we're going to have a parabolic shape. So you should have your potential energy rising from some maximum value down to 0 there, where it loses contact. So what about the kinetic energy then? So the kinetic energy is 1/2 mv squared. And there's a lot you can go through to show, basically, sorry, put that on the screen there, to show what the shape should be. But you should basically realize this too, that the overall energy can't change. So whatever we're dropping in potential, we got to be gaining in kinetic. So for the kinetic, we should start at 0 right when we release it at negative d, and right when we get to the original 0 point, it should all be in the form of kinetic. So it should take the opposite shape there. Even though they don't ask for it here, you can sort of imagine it as if we're keeping the total amount of energy same right there, where that purple line I just drew would be the total amount of energy. So how do I break up the points here? One for basically showing me potential goes from a max to 0, and that same one is for showing that kinetic goes from a 0 to a max. So 1 point for showing how these sort of swap positions there. The other point is for the shape. So if you drew them as straight lines, you'd lose one of those 2 points there. In that case there, they should be parabolic. And again, the easiest way to see it is for the spring, and that necessitates that the kinetic energy is parabolic as well. So the other 5 points here, that's 2 of the 5. One is you should show that the potential energy due to the spring remains 0 from that point on. So, because if it's not going to give it any mass, then there's no energy to be maintained in there. The other one is that the kinetic energy, because it goes across the rough part, it's going to have an outside force doing negative work, taking away its energy. So it's going to slow down and stop at 3D, so we're going to lose all of our kinetic energy down to there. So that's another point. So that's point number 4, that we lose kinetic energy. The last point is the shape, and the shape is linear, not a curve. How do we know that? Well, we know that work is equal to force times distance. The force will be a constant because it's just the friction force. So in other words, work is proportional to force there. Work is proportional to distance there. So, but work is equal to the change in kinetic energy. So the change in kinetic energy should be proportional to the distance, in other words, linear. So the last 2 points on this one are where they talk about the student saying, well, what if you compress it instead of 2D, you compress it further there? Where should it slide out to? And the student's saying, well, I think if you compress it 2D twice as far, it should slide twice as far, 6D, because it's going to have more energy, and therefore it should slide twice as far. So what aspects are correct? 1 point for saying that because of the equation, and you can cite it here, that a bigger compression distance means more energy. And that's basically all you need to say. But then what do you say that's incorrect? Well, because it's x squared, the spring energy is proportional to the distance squared. So if we compress it twice as much, we actually have 4 times the energy and therefore we should go 4 times as far as we did before. So since we went to 3D before, we should go to 12D. Now you don't even have to actually say all that to get this point. You just have to say, well, because it's x squared, it's not a linear relationship. You don't even have to say that it's 4 times, although that would be nice to say that.